Great.
Okay, can I start? Okay, so let us go on. And now I want to talk about the reason, at least, why for me, but also for a lot of people, elliptic curves are important, because they turn out to be very important and in some sense natural objects if you want to study problems related to number theory. I mean, as I was saying before the registration came back, in modern number theory, most of the times you cannot avoid geometry and algebraic geometry. Think, for example, about Pythagoras theorem, in the sense that if you want to find infinitely many integer triples which satisfy Pythagoras equation, so you want to find infinitely many and non-trivial things which satisfy this. When I say non-trivial, also meaning that I do not take multiples of these things. Then, okay, there are many ways to prove this, but an easy way is to use geometry, in the sense that when I start from this equation, actually, if I divide by this, it means that I'm studying what are the points with rational coordinates of the unit circle. And so you have to take to see if this thing contains infinitely many rational points. And it is easy to do this if you use the stereographic projection, because by doing the stereographic projections, you write the equations associated to the stereographic projections, and you can see there exactly a bijection, or at least a correspondence between take any rational number here, you get a point with rational coordinates here, and vice versa, if you start from a point with rational coordinates here, you get a rational number. So you see you have infinitely many rational points. And this is an example.
I have a stupid question.
Yes.
I learned about this example from a YouTube video, and I think why don't they teach it more often? Because it's incredibly funny and it's incredibly tricky.
I don't know.
In standard courses.
That's an interesting question, in the sense that
that's an amazing example.
It's really easy.
It's an amazing example.
Exactly. There are many easy things that are not explained in basic courses, and I don't know why. I mean, probably you also have to be interested in number theoretic things, in the sense that probably if you're more an analysis guy, you're not really interested into integers that satisfy the Pythagorean triples. But I mean, in a basic geometry course, I would explain this just because it's very quick and gives an insight into arithmetic geometry.
Yeah, I think it also gives an insight on why one should care about rational morphism or something like stuff.
Yeah.
And, it's basically explaining that the stereographic projection, which is straightforward, is a rational morphism, and it has this.
Exactly.
Which is, I think, cool.
And in the end, people sees stereographic projection in topology courses. So this would be just maybe an easy exercise to add for the students, to say, hey, with this thing, you can immediately prove this. And you see here the fact that I used the unit circle, so the curve of genus 0. What if instead now I use the curves with genus 1, the elliptic curves? And in fact, this is really fruitful, in the sense that a lot of number theoretic problems are reduced to try to do something like that on elliptic curves, to find rational points on elliptic curves. And I can give some examples. The first example is really basic, in the sense that the problem is find all cube integers and rationals such that they are equal to a square, a rational plus 2. Okay, this is not really strange in the sense that this is exactly try to find the rational solution of this, which is exactly try to study this elliptic curve and to find all the integer and rational solution of this equation. Okay, this is not very strange in the sense that the problem is exactly this. There is no strange transformation. I would say that the interesting thing about this problem is that the integer solutions are just finitely many, and in fact, they are just these ones. And proving this actually requires no geometry. You can do this by only using algebraic number theory, standard algebraic number theory, like work with cyclotomic numbers or stuff like that. No, maybe not cyclotomic, just work in this field. If you work in this field, then you can obtain that the integer solutions are just these ones. More interesting is what happens for the rational solutions, in the sense that you can prove, and in order to prove this, you need really the geometry of the elliptic curve, that there are infinitely many such rational solutions, and that if you take the group of solutions with q coordinates, the group is in fact infinite and cyclic. And this is a typical example with elliptic curves of I wanted to study the group of rational solutions. This group is called the Mordell-Weil group, and it's a very central object in the theory of elliptic curves. And in fact, it's the object which is related to the millennium problem, the one about the Birch-Swinnerton-Dyer conjecture. Because what you want to do in this problem is to find the structure of this group for every elliptic curve. Yeah. Then, okay, I can give a second example now of a number theoretic problem, which is related to elliptic curves. And this example is less obvious. I mean, it is less obvious its link with elliptic curves.
This and smooth structure one.
Yeah.
Only smooth. Very smooth case or for single case.
No, the fact is that the group here, I'm just seeing as an abelian group. Okay, the Mordell-Weil theorem states that this is a finitely generated group. We always know that. So it will be always a finite power of Z times a finite group.
But the elliptic curves are always smooth, yes.
Yeah, exactly. They are always non-singular over the specific field. Okay, the second example is the problem of rational triangles. Which is take a right triangle with area, which is, I can say, a natural number D. The problem is, can you find such a right triangle with sides A and B and C, all rational numbers? Can you construct such a right triangle with this area and sides which are rational numbers? This is an interesting problem which goes back even to Fermat, because Fermat proved that such a triangle exists. If you take, for example, D equal 1, it is very easy to prove it if you take D equal 6, but for generic D, sometimes you can prove that it is not possible, otherwise you can prove it is possible. But the very interesting thing is that, okay, now I do not have the time to explain the steps, but they are not difficult. The idea is that you can construct such a rational triangle if and only if you can find certain solutions of this elliptic curve. Y square equal to x cube minus d square x. And in particular, you can find rational triangles if and only if you can find solutions of these which have y coordinate different from 0. So you do not just need to have a solution, but also a solution like this. And this is also nice from an algebraic point of view, because if I consider the group of Q solutions of my elliptic curve, then by the geometric group law, it is not difficult to prove that a solution of the form x0 is a two-torsion point. Meaning that if I sum this point with itself, I obtain exactly the infinity point. So constructing a rational right triangle is the same as saying that I can find points in my elliptic curve which are not of two torsion. And so again, the geometric problem becomes an algebraic problem over the elliptic curve. And okay, I said a wrong thing about Fermat before, in the sense that when I take d equal 1, it is impossible to construct such a triangle. I confused the things. And in fact, when I take d equal 1, is the one curve I already we already seen during today. And if I look at the Q rational points, the Q rational points of these.
Sorry, I think that the video. Okay.
Okay.
Now
Is
it's good.
Is it working now?
Yeah. Thanks.
Okay. So I was saying, Fermat actually proved that it is not possible to construct this triangle with d equal 1, because with d equal 1, you have this curve. You take the group of Q rational points of Q solutions, and this group is isomorphic to this. The group of 4 elements, the Klein group, which only has elements of order 2. So this gives the solution for the Fermat case. In my knowledge, there is not a result for generic D. Yes, every point here is a two torsion. Okay, so this was the second example that you see. It's not so obvious that you can relate this thing with an elliptic curve. You can do it because it is that, for example, if you start from a solution here, then you take something like one side is 2xd over y, and the other one is x squared minus y squared minus d squared over y, something like that. You take the absolute values, and then you can see they verify the relation. But you see, this is not obvious. This is one reason why elliptic curves are interesting. And the third example, which is probably the most famous one that I want to briefly mention, it's Fermat's last theorem. So the statement of Fermat's last theorem is that if I take this equation in integers, has only, okay, here I take 3, but I can take actually any number bigger than 3. So let us write n here with n bigger than 3, has only trivial solutions, meaning that at least one of the solutions must be 0.
There is some question from whom? No?
Okay, so this is the classical statement of Fermat's theorem, and I mean, a first reason why this is interesting is that it's a clearly different behavior from the Pythagorean theorem we have seen before. With n equal to, you get infinitely many solutions very easily. You raise the exponent, and already this is not true. Then we know that Fermat claimed that he had a proof of this, but the margin of its book was not long enough. And I mean, we can almost surely say that he was wrong in the sense that probably he had a proof, but it was a wrong proof in some subtle things, in the sense that probably it was not a stupid thing, but probably it was really subtle in the sense that in 300 years, a lot of people have come with different interesting proofs that became wrong only because of very tiny and subtle things, which in fact originated algebraic number theory. Like we started considering cyclotomic fields because at some point Kummer noticed that when you take the Fermat equation with a prime exponent, you have to consider the p roots of unity, and this for generic prime p deletes the unique factorization.
Yeah, that's another problem. So that I could ask the same question as before. Why don't they teach that much of the Kummer factorization using cyclotomic?
I mean,
more or less
you can see this in any algebraic number theory, in the sense that usually people, when introduces the cyclotomic thing, mentions this factor. Because in fact, also the fact that you talk about ideals in algebra comes from this, because they started talking about ideal prime numbers, meaning prime elements that behaved exactly like primes in Z, and then Dedekind from that abstracted to the idea of ideal that we use now. And okay, there could be a lot of things that we can say about Fermat last equation. Also the fact that in fact, people became obsessed with that also because of an economic reason, because Wolfskel in the 19th century, in fact, he did not shoot himself because he really wanted to make it over, but at some point he started studying Kummer's work, and instead of killing himself, he was so happy with working Kummer's work that decided, okay, I will leave all my money to whoever will be able to resolve this. Wolfskel. He was not a great mathematician, but he was quite rich. So yes, there was also the problem that in the end, the amount of money that he left was completely not valuable when Wise and Taylor solved this, but because of the German inflation between the two wars. But this is another thing. Okay, but I think it was in the end something like probably $100 in the end. Okay, but what is the connection between this equation and elliptic curves? This was the, in some sense, outstanding thing that emerged during the 90s, during the 80s actually, 70s, 80s, because if I remember correctly, okay, this is the thing, was Ray, who noticed in, I think, was 84 or 85, something like that. It is actually a very recent. The connection with elliptic curves is really recent. Yes, in the sense that he noticed that assume that you have a solution. So assume that A, B, C is a non-trivial solution. Consider then this elliptic curve. Okay, you can always reduce to exponent which is a prime p, because if you can prove the theorem for prime exponent, then you immediately have it also for general exponent. This is easy to verify. So assuming you have a non-trivial solution, then you can construct this elliptic curve, and then this is indeed very technical and very difficult, but what happens is that, okay, I call this curve E.
So, and the fact that you can generalize this thing over any integer, like if you prove a prime, then you can also take
Yes.
and requires factorization.
I mean, it's just that, yes, if you take n, which is p times q, then if you have a solution A, B, C, for example, for p, you just need to take yeah, I guess
It's not already anything. Okay. Yeah, then
yes, yes, I'm just considering the normal integers. Yes. Yes, you just have to take from a solution, you get immediately another solution, which is solution elevated to a certain exponent, just to match the things. What do you want to have? You want to have p in the end because you want to reduce to the p1. So what you want to do, yes, stuff like that. Okay. Okay, I was saying that if I take this elliptic curve, assuming that this is a non-trivial solution, then what happens is that for some technical reasons which are very difficult to explain, then this curve E would be an elliptic curve defined over the field of rational numbers, which is not modular. What does modular mean? This is a technical thing in the sense that there was this conjecture by Taniyama and Shimura. I think it's from the 50s or 60s, which states that every elliptic curve over the rational numbers is associated to an object which is called a modular form. This is the meaning. I mean, there is a precise meaning of that, very technical, but the idea is that every elliptic curve is associated to something that is called a modular form. This is called being modular for an elliptic curve. And people wanted to prove this, and Frey noticed that if a non-trivial solution of Fermat exists, then the arising elliptic curve would be an example of elliptic curve which is not modular. And what Wise with decisive help from Taylor did was to prove that in fact Taniyama Shimura, it's true not in general, in the sense that they did not prove this in general, but for the elliptic curves also of related to Fermat problem. In the sense that they proved that a class of elliptic curves which are called semi-stable elliptic curves are modular, and the fact that semi-stable elliptic curves are modular force, in fact, this curve, exactly this one, to be modular, which is a contradiction then with the fact that we have a non-trivial solution of this. Here I mention the contribution by Taylor because Wise did really an amazing job something very titanical, incredible. But the fact is that the first proof he gave was not complete. He noticed this thing only after he presented it in a seminar. And he spent, I think, another year just trying to fix that. And he did it, but he did it also with help from Taylor. So Wise, yes, I think he did 90% of the work. So, and he deserves all the critical acclaim he gets. But the contribution from Taylor is really, really important, at least for this problem. And I also want to say that now the Taniyama-Shimura is known to be true. In fact, a few years later, after from this result, I think this is from 93, 94. In 2000, 2001, a lot of people, including, I think, again, Taylor, proved that the Taniyama-Shimura is true. Okay, so this is the important reason why elliptic curves are related to the Fermat problem. And the study of this connection, in fact, originated a lot of interesting but very difficult mathematics with a lot of concepts, a lot of tools. And now what people are trying to do is, for example, because here we just take Q, but nobody forbids you to take here, for example, Q of square root of 2, Q of I, other number fields. And people, again, are trying to say, can I obtain a Taniyama-Shimura over these different fields? And a lot of great mathematicians of today, like Anna Karagiani, Jakob Zimmerman, a lot of people are working on this. I think they are proved now that maybe all real quadratic fields satisfy Taniyama-Shimura, something like that. Probably also imaginary quadratic fields. And they're trying to work with other fields. Okay, and now in these last few minutes, I think I will take at most 5 or 10 minutes, because I just wanted to briefly explain 2 reasons why elliptic curves are important, not only for abstract number theory, but also for computational number theory and cryptography. I will be quick with this, but this is important. I would say just 2 things. The first one is that, okay, you know, I mean, the most difficult problem in computational number theory in the end is always the factorization of the integers. In the sense that you can think of a lot of results in number theory, but not only number theory, which are very easy and very elegant, but there is always one caveat that is you need before to compute the factorization of an integer number. And this is a painful task. I want to mention that, okay, there are nowadays a lot of different algorithms for computation of the factorization of an integer. One very interesting algorithm was developed by one of the Lenstra brothers in, I think, the 80s. And I think he was Hendrik Lenstra, yes, one of the Lenstra brothers. He gave a probabilistic algorithm to compute the factorization of an integer, which uses elliptic curves. The idea is that if you want to factorize an integer, then you choose an elliptic curve which you associate to this integer in a certain way, and by using the computer, you start to sum points of this elliptic curve and try, whenever at some point it happens that during the sum there is something wrong, then this something wrong is with high probability related to a factor of the integer. And so you find a factor. This is not deterministic in the sense that there is no proof actually that what you get is always the factorization of the number. But the probability that the factorization is true is computed and is really high. And in practice, it seems that these have never failed. And I think, in fact, most of these things of factorization now are dealt with probabilistic algorithms, because deterministic ones take too much time to give an acceptable result. You just need to assure that your probabilistic algorithm is strong enough to give a confident result. So not something that gives you the correct result in 50% of cases, not something much stronger. And the second application is okay, you probably heard about public key systems, like the most famous one is the so-called RSA, public key system in cryptography, from, this is Adelman, this is Shamir, I think, and this is Rivest. Just remember Adelman, I don't remember if I said the names correctly. That in fact, they obtained an interesting and very strong cryptographical system, which is based upon the fact that, as I told you before, it is very difficult to factorize a large integer, even if you know that it is the product of two primes. It is very easy to go this way. If you have the two primes, just multiply. It is very difficult to go this way. If you have the number, try to factorize it. And why this is called a public key? Because in this cryptographic system, this is public, this is known. Everybody doing working in the system, exchanging the messages in the system, knows this number. But the two primes here are secret. You can recodify your message only if you have, I think it just needs, yes, one of the primes is needed, but you need to have at least one of the primes. This is a very successful cryptographical system, but it is also a very heavy cryptographical system. When I say heavy, I mean from a computational point of view, also in the size of the messages that you have to send. And what several people did, I think at the end of the 90s, and probably also involving people like Koblitz, so very big names of elliptic curves, was to define a public key system with elliptic curves. So instead of just using an integer and looking for its factorization, the problem now is you have these public elements, which are a finite field, FQ, an elliptic curve over the finite field. So this is a finite number of points, but Q may be big, so this may be a big number of points. And a point on the curve. These are the public data. What are the secret ones? The idea is that now the secret is that you have Alice and Bob, as always in cryptography, that want to send messages. They share this common knowledge. What they do, they try, for example, Alice will choose an integer m and will sum p m times with itself and will send this to Bob. Then Bob will try to do the same thing with another integer. Let us call this q. N times q will do a similar thing and send it back. And the fact is that using the properties of the group law of an elliptic curve, by doing so, they can recover the original point by just knowing the original data. There are actually many other details that I would have to say to explain in detail what happens here, but in some sense, it's the same thing as here, in the sense that you are starting from something which is known, but everyone manipulates it in a private way, and you who have the secret keys can go back to the original point because you have the secret keys, and the secret keys exploit the group structure here. And why was this important in the end? Because, okay, it works and it's safe just as RSA. But the most important thing was that it's lighter, in the sense that it takes less operations, and the messages it sends are, I think, 5 to 10 times lighter than the messages sent with this system. And in fact, I think this was developed especially thinking about mobile phones, cryptography for mobile phones, because you needed a system not heavy as the one for the computers.
Where did you put the data? Is it the password of the data? Or?
I mean, yeah, the data is like, yeah, this one, in the sense that you start from the public thing and then you choose an integer, which can be a number. I mean, whenever you insert a thing like a password or a message, it gets converted to a number, and you use this number to do this sum.
It's like you can also send text messages.
Yes, exactly. The idea is exactly that you convert a text message or an order or something like that in a number, and then you use this number to do the operations. Okay, so this was a brief excursus about over the main features of elliptic curves. I think most of the times, I think in the next lessons, most of these features will be developed more in detail. And I think the next one is up to Martina, if I'm not wrong. So in the next lessons, we will be seeing more about the geometric features of the elliptic curves, and then more about the arithmetic features of the elliptic curves. And I think that for today, we can stop here. Thank you very much.
There is time for one question.
Magari ce le mandano per messaggi vocali.
Okay.
Se hanno domande da casa.
I think that no, it's
Probabilmente era solo un applauso.
yeah.
Sì.
Thanks
Applausi,
again,
applausi.
Francesco. Ciao a tutti.